So, okay, as you can recall, the last class, I drew this particular table, and after that, I started the discussion on the duality theory. Now, today I'm going to discuss about the table. The last class, I actually avoided that. My today's topic is still duality, and today I'm going to give you the idea about the formulation of the model, and I'm going to tell you how from a single physical system, two different problems can emerge. Now, as you can see in this particular table, some food items are given, which are denoted by Roman 1 and 2. And in these food items, these nutrients A, B, C are present in some units. So 2 units of nutrient A is present in food item 1, 2 units of nutrient B is present in food item 1, and 1 unit of nutrient C is present in food item 1. And similarly, in food item 2, 1 unit of nutrient A, 3 units of nutrient B, and 1 unit of nutrient C are present. And for an animal, minimum requirement for these nutrients are as follows. 14 is the minimum requirement for nutrient A, for 22 is the minimum requirement for nutrient B, and 1 is the minimum requirement for nutrient C. Okay, so minimum requirement of each nutrient for one animal are present and are given in this particular row. And these are the market prices of unit quantity of each food item. So market price of this food item 1, unit quantity of this food item 1 is 3, market price of unit quantity of this food item 2 is 2. This is the chart. Now, this is the background of the problem that I'm going to discuss today. Okay. Now, from this, we can formulate 2 different types of problems. We can visualize the problem from 2 different perspectives. One perspective is of the perspective of the dealer, and another perspective is that of shopkeeper. Now, what the dealer is saying, let me just read it out, and meanwhile you can copy it also. The dealer's problem is as follows. He wants to fix maximum per unit selling prices. He wants to fix maximum per unit selling prices of the 3 nutrients A, B, C such that the resulting prices of the food items do not exceed. I'm highlighting some important points. Resulting prices of the food items do not exceed the existing market price. Okay, these are the constraints. At the same time, he gets maximum sale price, which he wants to denote by capital Z. So he wants to maximize his sale price. This is the problem of the dealer. What is the problem of the shopkeeper? Now, the shopkeeper wants to do it in the following manner. He wants to determine the minimum quantities of the 2 food items to be made so that the minimum requirement of the 3 nutrients for each animal is met, and at the same time, the cost W of purchasing food items is minimum. So I'm highlighting the important points over there also. So according to the shopkeeper, he wants to minimize the purchasing of these food items, and at the same time, minimum requirements, minimum quantities of the 2 food items to be made in such a manner so that they must satisfy the minimum requirement of the 3 nutrients for each animal. Okay. So one after another, I'm going to discuss this particular problem. First of all, we will talk about the solution of the problem 1. Okay. I hope you have taken the screenshot. So I'm going on to the next page. I'll again come back to this page. If you're writing, then I'll be able to write it later. So you can just quickly write the statement given in problem 1 and the table. Now, if I talk about the solution of the problem 1, immediately we can say that this problem 1 is a maximization type of problem. Okay, and he wants to maximize the sale price. Okay, so how to start formulating the problem? Let's begin. Let x1, x2, x3 be the prices per unit of the three nutrients. A, B, C respectively, that are to be fixed by the dealer. Okay, so the problem is to find x1, x2, x3, which are of course the decision variables, which will maximize the sale price. Now he is denoting the sale price by capital Z. So immediately he can write max capital Z. Capital Z is the sale price. Remember, capital Z here is the sale price. He wants to maximize it, and that sale price is given by 14x1, 22x2 plus 22x2 plus 1 into x3, that is x3, simply x3. Okay, this is the sale price, because the sale price of these items will be dependent upon the nutrients present in these food items. Okay, so this is the sale price. x1, x2, x3 be the prices per unit of the three nutrients, per unit prices of the nutrient A, B, C. So if per unit price of the nutrient A is x1, so 14 units of nutrient A will be 14 into x1. Per unit price of nutrient 2B is 22, then x2, then 22 units of nutrient B will be having price 22x2. Per unit price of nutrient C is x3, so 1 unit of nutrient C is obviously x3, and that will decide, the total of this will decide the maximum sale price. This objective function is subject to the constraint. This objective function is subject to the constraints. What is written? He wants to maximize his sale price so that the resulting prices of the food items do not exceed the existing market price. So these are the existing market price, remember, for each of the food items. And I am considering these units, 14 units, 22 units, 1 unit, together considering the food items 1 and 2. Now, if I individually consider the food item 1 and food item 2, so similarly, we can say that for food item 1, if x1 is the price per unit for nutrient A, then that price for that price will be, with respect to food item 1, the price will be 2x1. For food item 2, that price will be 2x2, and food item C, the price will be x3. If I consider the food item 2, similarly, we can say that the price of nutrient A will be 1 into x1, that will be 3 into x2, that will be 1 into x3. And these prices for each of the food items should not exceed the marketing price. Therefore, the total of the prices for the food item 1 will always be less than or equal to 3. Total of these prices for food item 2 will always be less than or equal to 2. So from this analysis, we can get the constraints as the following. We get 2x1 plus 2x2 plus x3 less than or equal to 3, x1 plus 3x2 plus x3 less than or equal to 2, and x1, x2, x3, these are the decision variables, and therefore these are non-negatives. This is the market price constraint for food item 1, market price constraint for food item 1, and this is the market price constraint for food item 2. These are the two constraints, and we are done. We have got our objective function, we have got our constraints, we have got the decision variables. Now, before I move on to the next problem, I mean the problem of the shopkeeper, let me quickly find the dual of the given problem. Okay, by the analysis that we have learned in our previous session, previous class. Now, to find the dual of the problem, what we need to do, we need to transform this equation, this model into its matrix form, as you know. So we can write this, step number 1, we can write this as max of z, this matrix 14, 22, and 1 multiplied by the column vector x1, x2, x3, and subject to the constraint, this coefficient matrix you write 2, 2, 1, 1, 3, and 1 multiplied by the column vector x1, x2, x3 less than or equal to 3 and 2. This is the matrix. The order of the first matrix is 2 cross 3. Order of the second matrix is 3 cross 1. Number of column in this matrix is equal to the number of row in this matrix. And the order of the right hand side matrix is 2 cross 1. Resulting matrix on the left hand side is also 2 cross 1. And this column vector x1, x2, x3 greater than or equal to the 0 vector, which is 0, 0, 0. Matrices are often termed as vectors. Okay, remember. Now, as I told you that if it is a maximization type of problem, then by convention, we always try to keep the inequality of that of less than or equal to type. Okay. Then we can convert the inequality into something else. Suppose in the dual problem, in the primal problem, the inequality is a mixture. Some inequalities are less than, some inequalities are greater than, some inequalities are equality. Then we have to do something to bring all the inequalities into a lesser than type inequality. That I'm going to explain today later on. But here there is no trouble, because already the constraints are all lesser than type of inequality. So directly we can write the dual as the given by the previous rule that we learned in the previous class. So in step 2, we know the dual of the problem will be minimum of z. So z will be replaced by some other new variable. So the variable here is w, say, and in place of this, I'm going to write the matrix 3-2. That means the transpose of the matrix 3-2. 3-2, row 3-2 is the transpose of the matrix column 3-2. And how many variables will be there in the new formulation? Since there are only 2 constraints, so in the new formulation, the number of variables will only be 2. So we can write it as y1 and y2. Y2 variables, because here the number of constraints in the primal problem, if this is my primal problem, here the number of constraints is only 2. So the number of variable in the dual will be 2. Subject to, in place of the coefficient matrix, what we write? We write the coefficient matrix transpose. So we write it as 2, 2, 1, 1, 3, 1, transpose of the coefficient matrix whose order is 3 cross 2 multiplied by the column vector y1, y2 whose order is 2 cross 1, so that the number of column is equal to the number of rows in the 2 matrices, which is and the symbol, the lesser than type of equality will become greater than type of inequality in this particular problem. So we write greater than type of inequality. This is the conversion. And on the right hand side, we write the transpose of this matrix. So we write 14, 22, and 1. And y1,
Sir,
y2, yes.
স্যার বলছি 2 1 এই সাবজেক্ট টু ওটা তো বুঝিয়ে দেবেন স্যার আরেকবার সাবজেক্ট যেটা করেছেন
Yeah, you
নেক্সট স্টেপটা
yeah. If the primal problem is of this form, max z is equal to cx subject to the formula I'm writing right now, subject to the constraints ax less than or equal to b, x greater than or equal to 0 vector. If this is the primal problem, then it's, suppose this is the primal problem, then its corresponding dual problem will be mean of w b transpose some other vector y subject to a transpose y less than type of inequality becomes greater than type inequality, and in place of b we write c transpose and y greater than some 0 vector. This is the formula. Now c is here, the c matrix is this matrix, capital X is this one, capital A is this one, this is the B matrix. Okay, now you see in place of C we have written B transpose. This is the B transpose part. B transpose means all the rows become column and all the columns become row. And in place of B we have written C transpose. Just look at this. 14, 22, 1 was a row matrix in the primal problem. Now it has become a column matrix in the dual problem, and it comes in the constraint section. 3, 2 was the column matrix in the constraint section. Now it becomes a row matrix in the dual problem, and it comes in the objective function. That's how we interchange the thing, 2 things. So this is the thing, that is the dual of the given problem. Okay, now I'm not going to calculate this dual right now. If I multiply the matrices, you can easily do the multiplication, but I'll show you. I'll show you later on. Yes,
sir.
Yes.
Sir, suppose if item 1 here will be 2x plus 2x1 plus 2x2 plus x3 less than equals to 3, but suppose in item 2 it is not less than, suppose it is greater than equals to, then in subject to matrix condition, what should I get this sign, greater than equals to or less than equals to?
I said that that particular part, that when there is a combination of things like greater than, less than, equality, that part has not yet been discussed. I'll come to that part later on.
Okay, sir. Okay.
Right now my objective is to show you what is my objective. Yes, in the last class I showed you that what is dual, how to construct dual, the easiest form of the dual problem derived from the primal problem. I showed you greater than becomes less than, column becomes rows, rows become columns, etc. I'm sticking to that right now only. Here, my first objective of today's class is to show you the how this primal problem and dual problem evolve from a given system, physical system, from a given problem, physical situation. So in the initially, to start with, we have considered a physical situation, a food item problem, a nutrient problem, whose background is given in the table. Now, we are going to visualize the problem from two different perspectives. The first perspective is the perspective of problem, which is problem one, which is the problem of dealer. Now, according to the dealer's perspective, I have formulated the primal problem. Fortunately, in this primal problem, all the inequalities are lesser than type of inequalities. And now I'm mathematically constructing a dual problem, that if this is the primal, that is the dual. So right now I'm going to tell you what is the meaning of this dual, the dual that I have obtained over here. What is the meaning of this? Okay, so why do I convert a particular primal problem into a dual problem? Is it the conversion possible? Why do I convert? So physically, we are now going to discuss the problem of shopkeeper. So first of all, I'm going to formulate the problem of shopkeeper now, and then whatever there comes in the problem, we will try to connect the formulated problem of the shopkeeper to the dual problem that has been obtained mathematically in this particular page. So right now I'm saying that if step one is the primal problem, step two is the dual problem of the given physical situation. Now let's get back to the problem. In the problem, it is written that we are going to consider the case of shopkeeper who wants to determine the minimum quantities of the two food items. Okay, so this is my starting point. So I'm going to formulate this particular problem by considering the quantities required for the two food items, so that the minimum requirement of the three nutrients should be met. So we will try to understand this particular thing with help of some equations and inequations. So first of all, if I go to the solution of the problem of shopkeeper directly, problem 2. So let's talk about how to formulate that particular problem, problem 2 solution. In problem 2, we are going to consider two variables, say let y1 and y2, and let this be the units of food items 1 and 2 respectively, which are made for each animal. Okay, now you see that the shopkeeper's problem is a minimization type of problem. What he wants to minimize, the cost W of purchasing the food items. So his problem is a minimization type of problem. Here the problem that I'm going to consider is a minimization type of problem. And we can formulate it in the following manner. Since the cost is denoted by W, so we write minimize Z, minimize W, minimize cost. And you see, just look at the table. The market price per unit of the food item is 3 and market price for the food item is 2. And we have considered Y1 as the units of the food item 1 and units of the food item 2. So if 1 unit of the food item has market price cost 3 and 1 unit of the food item has market price 2, then Y1 units of food item will have market price 3Y1 and 2 units of food item 2 will have market price 2Y2. So total cost of the food items together will be 3Y1 plus 2Y2. Okay. Subject to, now just look at the table. If I consider the columns for nutrient A, nutrient B, and nutrient C individually, we have to maintain the minimum requirement of the nutrients in the food item. So if I stick to the nutrient A, then for this particular column only, to maintain the minimum requirement, we must write it in the following manner. We must write that it's subject to the constraints 2y1 plus y2, and the minimum requirement is 14. So it should be greater than or equal to 14. So minimum 14. If the requirement is high, if the amount present, the amount of nutrient present in these food items is higher, no problem. But the minimum requirement is 14. It should not be less than that. Therefore, greater than equal to sign is coming. For the second one, we need to consider the second column. That is for the column for the nutrient B. So if I want to maintain the minimum requirement, it would be 2y1 plus 3y2. This should be greater than or equal to 22. And for the last one, we have to consider this particular column. So that would be y1 plus y2 greater than or equal to 1. And obviously, y1, y2, y3, these are greater than or equal to 0. So this is the problem, formulated problem, formulated mathematical model for problem 2. Let us now try to look at the matrix form of the given problem. So the matrix form of the given problem does look like this. So we write min W. This would be 3, 2, y1, y2, subject to write the coefficient matrix 2, 1, 2, 3, 1, 1, multiplied by the vector y1, y2 greater than or equal to 14, 22, and 1. And this vector y1 and y2, these are greater than or equal to the 0 vector or 0 matrix. Now just look at this particular matrix. Look at this particular formulation and look at this particular formulation. They are both same. This is the thing that I wanted to show you in the first session of today's class. The two formulated problems. Here we have first formulated the problem from the shopkeeper's point of view. Then we have written down the formulated problem in matrix form. And in the previous page, we wrote the problem in terms of, we formulated the problems from dealer's point of view. We found the dual of the problem. What we are able to see over here is that the dual of the primal problem is actually the problem of the shopkeeper. So if the main conclusion is, if the dealer's problem is your primal problem, then the shopkeeper's problem is your dual problem. Now, there is no hard and fast rule for considering a particular problem to be a primal and another problem to be dual. So any problem can be a primal problem, any problem can be a dual problem. So if someone thinks that shopkeeper's problem to him is the primal problem, if shopkeeper's problem to someone is primal, then for him, the dealer's problem is the dual problem. Is dual. So I hope by this particular example, you are able to understand the physical situation, the physical system from which this two types of problem can emerge. Okay. Now almost the time is running out. So in the next session, I'm going to discuss about the answer to the problem that has been asked several times earlier. That if there is a mixture of inequalities like greater than or less than or equality, how can we deal with the situation? I'm going to discuss that in the next session.